I will be recording this session based on an email that I received. So let's see, most are joining, but we'll still wait for a few minutes to start the lecture. I'm gonna share my screen and put that away. This is my GA. I'm gonna run all code. No error messages there. So how is the progress on the test 2 project? I'm not sure if I understand your question, Alex. We'll have to make Sahil a function of M and N. The current version would, otherwise the only thing that is a function of M and N is the thickness, correct? That is correct, but based on thickness, also the stresses become a function of M and N. And when you input stresses to the module, you will get you will go to the Sahil module. There was something that I wanted to do for a while, and one of you guys reminded me that earlier this morning, and I think I am going to do that. In fact, I did it, and I will tell you right now what it is, and perhaps we will change the Sahil to another failure criterion, which is called SAIVU. And SAIVU is actually a generalization of the von Mises criteria to anisotropic medium, and it takes in the XT and XC and YT and YC as independent constants for failure, and it has one single equation. There are no ifs and buts in the module, and if we change to that, I'll show you what it is in a minute. That should work much better than trying to start tweaking the Sahil module. So I will have provide you the chapter on failures. Let me look at what I put out there for the untitled folder or in documents. Chapter 1 by Rudal, GA, effective properties, cost of composites, and in modules, strength. Under supporting documents, I have strength, and I do not have the chapter of the book in there. Let me, I didn't really want to get into the details of strength calculation, because that's really not the topic of this course. That topic belongs to introductory composites course. But let me go ahead and put a strength designers copied. I actually recently found the entire book on the web. So I didn't create this PDF file. I downloaded it from the internet. It has the entire book apparently copied, which is a good thing. As long as I didn't do it, I got it from the internet. I think I have the flexibility of putting this on my webpage now. And if you look at that, the chapters of that book, there is chapter 6, which is failure criteria for composites, starting page 223. And therefore, we start with isotropic layers and look at the max stress, max strain, Tresca and von Mises. Then it goes into failure of fiber reinforced, max stress, max strain, Sci-Hill and Sci-Wu. So Sci-Hill and Sci-Wu are actually discussed in pages 237 and 241 respectively. So I'm going to put this entire book in there. But if I go to page 241, which I'm going to make an attempt right now, that's chapter 5, and it's chapter 6. All right. And this is where the Sci-Wu criterion is introduced. This is the general form of the quadratic function, and there are these coefficients in there that need to be determined based on some thought experiments, and some of those thought experiments are discussed in this chapter. But at the end, you get a form which will be in this for Sci-Wu criteria. I don't know if you see the equation 6.2.33 in there. This is the Sci-Wu, and Sci-Wu has actually xt and xc and yt and yc and s explicitly in there. So there's only one equation that is programmed, and I actually put it into the composites module. So let me show that as well. Where is that? Files recently opened. CLT 4.3, version 4.3. And as you will see, that is a much simpler module. Find Sci and Wu. Failure. So this is a description. It takes the same input as sigma x, sigma 1, sigma 2, tau 1, 2, and also xt, yt, xt, xc, yt, yc, and ss, exactly the same way that you call Sci-Hill, and it produces one value. And the module is just this. Very simple, one line. Sci-Wu number is basically the sigma 1 square divided by xt and xc divided by yt and yc, and the cross term sigma 1 and sigma 2 has a minus sign and is divided by square root of product of xt, xc, yt, yc. Tau is the same way. And then there is 1 over xt minus 1 over xt sigma 1 and 1 over yt and 1 over yc sigma 2. So this is a much cleaner expression compared to this Psi-Hill envelope that has all these ifs. So if you switch to that, it'll be easier rather than starting to tweak this one and trying to compute. Now this will obviously compute if sigma 1 and sigma 2 and tau 1, 2 is in terms of either an m or an n. This will also compute that number in terms of m and n, because it doesn't have to compute any if statements to looking at the value of sigma 1 and sigma 2. As soon as the module starts looking at the value of sigma 1 and sigma 2, that will require tweaking this. And I suspect that if anything goes symbolic in here, it will immediately bounce from one of these statements that if this is greater than 0, because we don't know if it will depend on the value of m, and you can always try to tell that it's always positive, but that may still cause some complication in here. So you are free to actually play with this and see if you can make the Psi-Hill work for this problem. And but a simpler version would have been just simply getting rid of these ifs. And if you use Psi-Hill, reduce it to a single equation that is not dependent on xt or xc, and that is the case when xt and xc are actually equal to one another. So one equation that you can keep in Psi-Hill should do the work as well. Does that answer your question, Alex? Okay, you say here. Of course, you can, if you like, I can actually email this to everybody right now. And how do I do that? I go to what? Here. Okay. Ultra. I hope I have not lost you guys in the Ultra. I'm simply trying to go backwards in my notebook thing. Are you guys still there? Give me a sound.
We're still here.
Very good. All right. Except I don't know where I am. I thought I could find easily to send you emails. Homepage, courses, my announcement, my tasks. Maybe if I close this. This way. Under tools. No, not under tools. What am I doing right here? I'm trying to find the email page that I can email to everybody. And Matthew is already there as well. That's good. page, announcement, service discussion, send email. There it is. All users. Module. All right. I'm not sending it as a file. I'm just sending it as a text line. So this should work to determine the SIVU number. Submit. Gone. All right. Very good. Okay. So let's get out of here, and I'm gonna also post this entire book on the internet, and if you want to read about how you actually drive the SIVU failure criteria, you can read this section 6.2.3, and then the previous one shows it's SI-Hill, and it has some graphical comparisons of as a function of data that you can also take a look at and see the difference. This one for the tensile loading seems to indicate that SI-Hill and SIVU are very close to one another, and only in the compressive loads they start differentiating from one another for off-axis angles, and SIVU is not conservative. SI-Hill is more conservative than SIVU. But the difference is rather small, so they should work equally well. Very good. I'm glad you received the email. And let me also put this book on the contents. Course contents, course documents, supporting documents. I'll put it there. And earlier you had the chapter 1 that I generated the PDF, but now I'm gonna actually include when I open this build content file, red is my favorite color, and browse location of the files, courses composite design. This is done in spring 21, that should be in 2019. Oops, go and choose the file upload, submit. Okay, you will have the file posted in there. I did also put, I can put the program file, new version, in there. The programs. And this will be called version 2.3.4, but I think I made this 4.3, which is a version 4.3. And I'll put that file in there as well. That's in the Spring programs, CLT 4.3. While I'm at it, I'm going to also put the GA 2021 Unified, which is what I hope to start today. And I'm sure we will start changing it as we go along, because this is also this is a genetic algorithm that I've been putting together, and the file for that is latest update at 2:45, fresh off the oven. And there's the genetic algorithm module in there. All right. So with that, I'm going to go back to my lecture by minimizing this. And I'm happy to let you know that I survived this second COVID vaccination. Put me down for a day, but I hear that that's a good thing. I had reaction to both the first one and the second one, and I strongly encourage you guys to go ahead and get vaccinated, because it's available for you. You just go to the student services and you'll be vaccinated. There's no age thingy anymore in there, I believe. Is there anybody who hasn't vaccinated yet? Good. All right. Yep. Did you have a reaction to the first one? Very good, guys. That's interesting. Yeah, my son also had no reaction. But my son didn't have COVID. I did. Yeah, that's interesting. My wife and I had both COVID, and we both had reaction to the vaccine. All right, let's get back to our lecture. What we're gonna do today is, I believe I did not finish the...
It's currently partly cloudy and 84 degrees.
Who asked you? Did I tell you that joke? That this husband and wife has been talking to one another, and the husband wanted to say something sensitive, and he lowered his voice and started whispering to his wife. And the wife said, "Why are you whispering like that? Are you afraid of something?" And the husband says, "I'm pretty sure that somebody is listening to us right now." And the wife laughed. And she was, really laughing at her husband. And then the Siri laughed. And then what's the Google's program like Siri, that also laughed from the computer. It's a pretty bad joke, isn't it? I'm sorry, since I am back from being sick, I'm extra silly today. All right, lectures. Alexa also was laughing. Siri left and Alexa laughed. All right, so this is the GA. I'm going to ask somebody to remind me where I stopped. I think I went through these made some definitions there. And this is probably where I stopped. So this is a selection scheme. As I have mentioned, this is traditional hill climbing, jumping from one particular design to another. The GA works with a population of design. So if we have two design variables, x1 and x2, and if this is the design space and if this is the minimum here, initial population, or at some point in the evolution of the population, you may have 10, 20, 30, depending on the size of your population and depending on the number of design variables and depending on the granularity of this axis x1 and x2, you may have a large number of design points. And what the optimizer will do from this population, it will create a new population that will have better characteristics compared to this particular population. And to do that, it needs to choose the better designs. That's sort of the survival of the fittest. So those designs that are actually near the optimum solution should have a better chance of surviving into the next population compared to some design that's really out there away from the the best point. And this shouldn't have such a large opportunity to propagate itself into the new population. And the mechanism to do this is called selection. And it is done by computing their goodness, how good they are, their objective function, and start comparing them. So we first start an initial random designs, and this makes a population. So let's call the design 1, design 2, design 4. And this is a population. We evaluate how good these designs are. And let's say their objective function or their fitness is represented by lambda 1, lambda 2, and lambda n. This is after evaluating the objective function f at the design point specified here. At that point, we take those and construct what you can call a roulette wheel. Roulette wheel is tweaked in such a way that those designs that have better fitnesses would occupy a larger portion of the roulette wheel. This is not a roulette wheel that has equal slots to pick when you throw the ball. It turns around and around and falls into one of those slots. But if one design has good fitness, that particular design will have a larger slice of the roulette wheel. And to do that, we numerically, there's a scheme for that. We create an R number, R1 through Rn, where n is the population size. And each of those designs will have a value of its fitness divided by sum of all the fitnesses. Okay? And that gives you the size of the slice. All right. So let's say you have an initial population of some design represented by 1s and 2s and 3s. We don't know what they are. Perhaps they are angular orientations or some other alphabet that is specified in the design. But this could very well be a laminate if, let's say, 1s represent 0-degree plies and 2 represents 45-degree plies and 3 represents a 90-degree ply. This will be one stacking sequence, okay? And we go and evaluate its fitness. Let's say the fitness either the psi build number or some stiffness property, either bending stiffness or axial stiffness or whatever that number is. And let's say that number comes out to be 0.355. These are some normalized numbers. They could have been in the hundreds or thousands. They don't have to be less than 1. That normalization comes into effect when you use Ri, which takes that number and divides it by the sum of all the numbers. So let's say the second design has a very large fitness, 0.9, and the fifth design has pretty lousy fitness, 0.018. And you can see that they are randomly changing because this population is not ranked or anything. It's just random population of designs. Then if you do the fitness, the size of the slice, Ri, that will be this lambda divided by sum of these lambdas. It says 6 here, but 6 actually belongs to here, j from 1 to 6, lambda j. That's not lambda j divided by 6, that's lambda j divided by summation from 1 to 6 lambda j. And graphically, this is what it looks like. The first design is 0.355 out of sum of all of these. And that's this. Second design has the largest slice. That's this. Third design has a pretty lousy fitness or property, and that's this one. R4. R5 is really tiny slice. So either if I throw a ball that goes around and falls in somewhere, or I put an arrow someplace fixed and spin the roulette wheel, the chances are this R5 is not going to be hit by this arrow, but R2 and R6 and perhaps R1 and R4 are more likely designs to be selected. And this is the roulette wheel. And we spin this wheel 2 times with each time picking a new parent that we will be using to create next generation. Okay? So this is a selection process based on fitness. There are other versions of this, which I am gonna state here. Why not just directly select the cases with the highest fitness? All right. So Alex says, you know the highest fitnesses. Why don't you just select them? So the answer to that is biology doesn't do that. And there is a reason for that. There is a selection pressure in the process, and it has some random feature to it. We're simply increasing the pressure for the better designs to be selected. But no matter what, it is generally believed that even the poorest design may have some feature in it that if by chance it is selected, it can create a new genetic information that will be better than the available genetic information in the best parents. Okay? This is what the biology does, and we are going to actually give other examples of that in the coming operators. That sometimes it's actually not very good just to say, I'm going to take the first 4 best designs always, and I'm going to move with them. Because what's going to happen, for sure, is whatever the information is in this first 4 designs, R1, R2, R3, and R4, they are going to start governing everything. They're going to become the more and more dominant designs, and as they evolve, they're going to be completely overrun everything else in your population. And this is never good for any biological creature, because genetic information, it's so vast, it's so varied, that that sooner or later, one piece of genetic information may prove to be too valuable to actually miss. Okay, so this is the explanation that I can come up with from computational side. I am pretty sure that other scientists working in different fields may have looked at these kinds of things more thoroughly and have better ideas, but this is my explanation. And in fact, you will see these things in action. When you do these codes, you will actually find that some things will simply not work. You're going to get trapped in local minima, that you will never be able to get out of that local minima until you throw in there some new genetic information. All right, does that answer? What's an example of something created with a genetic algorithm? Biological genetics of all the creatures. It really is a huge string of DNA. Millions and millions. Billions. And we just evolved. That's called evolution. Now, if you don't think that evolution can do something like that, that's another story, but numerically it does. Something artificial. Something artificial created by genetic algorithm. I mean, these algorithms are actually used for a lot of things these days. They are used GA to optimize neural networks. Absolutely, that's one of the things that you do. Training networks. Artificial neural networks are mostly trained by these kinds of algorithms and the version that we're going to be looking at is actually not the best version for AI-type approaches. We need to go to really a large number of objective functions, so multi-objective formulations to do that. But yeah, GAs are used for that. In fact, if any GA book the AI book that you take, somewhere in there you're going to see a mention of genetic algorithms. They're not always called genetic algorithms. Sometimes they're called evolutionary algorithms. So evolutionary algorithm is a variant of what you might call genetic algorithm, or a genetic algorithm you may call one version of an evolutionary algorithm. But those things, yeah. What else are they used? Composite design optimization. They prove to be actually quite good in finding designs that cannot be otherwise found. But they're expensive. I haven't started complaining about genetic algorithms yet. They'll come later. They are very expensive algorithms. But you have lots of data, a lot of data, and they become very efficient. Other places that GAs are good. When you're dealing with functions that are very noisy, noisy functions or discontinuous functions, okay? The optimization algorithms that are based on mathematical optimization, mostly assumes the functions, objective functions and the constraints to be continuous, smooth, not noisy. if there are noises in the function going up and down, especially derivative information kills you. You can never converge to anything good. So GAs are perfect for that because they don't use derivative information. That information is built as the knowledge into the population. Also, discontinuous functions, the gradient information again is useless unless you're able to jump from one interval in the design space to another completely new interval. You cannot continue. And to show that, say in here, let's assume that this was a two design variables design space, and I'm going to draw a hole in there somehow, or a couple of different things. Let me see. To be able to draw, I need to go to this and get a black pen, for example. And let's say that this part of the design space was not available to you. Okay? This is simply, for some reason, is completely not available. Your functions don't work in here. You have no idea what's in there. So most search algorithms that does this kind of a thing will never be able to jump from this portion of the design space to this portion of the design space. Whereas GAs, based on these random features that utilize the best designs features and combine them with some other features. So when you combine a design that is in here and get a design that's in here and use them as parents to create a new child that will be in your next generation, the new design point might either be in here or in here. And that will be an advantage for you to keep interrogating the design space that are disjointed. So this is a disjointed design space, for example. There was a ping, so I'm going to have to keep this and get out and look at my ping. Interesting. So primary advantage is that it keeps you from being stuck in a local minimum. That is correct. That may not be the global optimum. That is absolutely correct. But is there 100% guarantee that it will always give you the global optimal? That is also not guaranteed. It all depends on how much money are you willing to spend on your computing time. The more time you spend, the chances are going to get better that you can actually find the global optimal solution. Also, multi-objective formulations. There's a different version of GA where the selection is not based on just fitness, but based on some Pareto optimality conditions that will allow you to have designs that improve multiple objectives at the same time, and they will evolve by interrogating multiple objective functions at the same time. So your design space are going to start forming Pareto fronts in the design space. But those are the details that may or may not be important for us right now for the GI optimization. All right, so continuing with this, there is a possibility that the pressure on selection of the better designs is not sufficient. Okay, and when will this happen? This will happen that the pressure may not be sufficient to choose better designs. This will happen if, for example, this roulette wheel, instead of being divided into various sizes, it is divided into almost equal sizes. Okay, so in one generation, you look at all the individuals, they're also very near the same number, that they all start occupying equal slices in the roulette wheel, which means that even a slightly better design has no chance of being selected out of those uniformly distributed fitness values. Just like better designs becoming dominant, If that happens, every new design that you're going to generate that will replace an old design will like to again occupy the same amount of slice. So you will lose that pressure. So you have to give, even if it's slight improvement, it has slightly larger value of the fitness function. You need to magnify that to make it more desirable to choose that design rather than some other design. In that case, one thing that you can do is basically you take the square of the fitness instead of the fitness itself to make the roulette wheel. Now, this happens again if highly fit designs start dominating the selection process, in which case, just like this case, we can do another selection scheme. And this is a scheme called rank-based selection. So instead of doing the roulette wheel segments based on their fitness value, we rank the designs and we give their ranking as an indication of their size. So when you rank them, the best design should have the largest number, say from 1 to 10. If you have 10 designs, your design number 1 will have the worst fitness. Your design number 10 will have the best fitness. In which case, this 10 is used as instead of its fitness value, and every other design is represented by their rank, which means that the roulette wheel sizes are fixed for the entire duration of your operations. Best design takes the largest fixed amount, the worst design takes the smallest fixed amount, and you keep doing the fitness selection based on ranks rather than fitnesses. So that's another piece of information. Instead of fitness-based roulette wheel, you do a rank-based roulette wheel. So how do we numerically imitate spinning of the roulette wheel? We define capital R numbers. Capital R numbers are summation of the small r numbers going from 1 to I. So R1, capital R1 is equal to small r1. Capital R2 is equal to small r1 plus small r2. Capital R3 is small r1 plus small r2 plus small r3. And the last r is sum of all of them. And then we flip our coin, create a random number r, and look where we are. If we are, I heard myself screaming. I don't know what happened here, but I was screaming. So if our random number is between this one and this one, then we take R1 as the parent. Okay. All right. So the R0 is you can assume it to be the base point. So R0 and R1, if that number is between, you take R1 as the selected design. Next up, okay, now we can choose parents that we are gonna bring together to create a new child, okay? And the biology does this with an operation called crossover. And the crossover is implemented numerically with a probability of crossover PC. This probability of crossover PC should be relatively high. The chances that the two parents are going to have crossover is very high, it's better than 90%. And if you don't, then you're not going to create children that are actually any different than parent 1 and parent 2. Crossover will create 2 children from 2 parents. And parents might be laminates. Let's say I have a laminate stacking sequence, and the first parent has 1, 3, 3, 2, 3, 1, which is 2 layers of zeros, 2 layers of 90, another 2 layers of 90, and then 2 layers of 45. That's digit number 2, and then another 2 layers of 90 and 2 layers of 0. This is a special version of this coding that ensures the balance condition of the plus minus 45 together. If you do it with 0 and plus 45 and minus 45 with different digits in here, then you will have to ensure some other way balance condition if you insist on balance condition. If you say, if I use 1 for a single 0-degree ply and 3 for a single 90-degree ply instead of 2, but say 2 represent plus minus 45, then your thickness will change from one individual to another based on the same length of stacking sequence. Your thickness will be different, and then the children that you're going to be creating are going to be different than their parents as well. So it's possible to do thickness variation by doing that way, but we'll see that we can do that in a different way, and we'll still be doing better than it's going to be more complicated to turn these into a single and leave this as 2. If we make this 1, then we have to impose a condition that for every plus 45 there must be a minus 45, which will require again tweaking with the genetic coding. For the simplicity, we are representing a stack of 2 layers with an integer here, and this simplifies the coding and everything else to be much more attainable. So what is crossover? Once you've decided that you're going to do crossover, you flip your coin one more time and choose a point of crossover. And then you take the parent 1, take the first portion of your, let me turn this into a pen so that we can also mark. And I'm going to do a red pen. So I take the first portion of the first parent, and we put it here. And I take the second part of the second parent and put it here. Those 4 numbers. So 1, 3 is here, 1, 1, 3, 2 is here. So the child has an entirely different stacking sequence for this balanced symmetric laminate. Entirely different properties, same thickness in this case. And child 2 is by taking this and putting it there, and taking this and putting it here. And this is child 2. So this is crossover. From 2 designs, we generated 2 designs. These were supposedly better designs for some reason, and that's because of special location of this information. It is possible that this design was good because it had a lot of 90-degree plies. Okay? This doesn't have a lot of 90-degree plies, but it has three 45-degree plies, or maybe 45s are outside, because relative location is very important in stacking sequence design optimization. So either the location or quantity of these different plies make them good designs. By doing this, even though we are destroying the string at an arbitrary point, those features associated with that might actually survive into this. Now, here obviously we went from 6 90s to only 4 90s. So we destroyed that information. Maybe this child will not be as good as parent 1. But there's also a chance that this may be better than the parent 1. And this is true for natural genetics as well. You can never tell what you're going to get. I know that for sure. I have 4 kids. So, the second child has 3 45s, just like its parent, and plus 45 is still outside, but it has also new genetic information that it has distributed the zeros towards the inside. Maybe that's good, maybe that's not good. We don't know. But it's interrogating the design space. It's a design space exploration. All right, so that's the crossover. Now, next operator. Any questions so far on this? I'm going to go to this. No questions, no things and anything. Next operator is mutation. Now, in regular genetics or binary version that we can implement, this is again implemented with probability. And probability of mutation is something low. It should not be high. And the reason for that is probability of mutation is going to require you to take the parents, parent 1 and parent 2, and apply mutation by flipping your coin again, picking a position, and changing whatever this genetic bit was to something different than itself. So you take this 3, you turn it into a 2, you tweak the design. Now, if you do this a lot, then every time your parents are trying to do something better, you're destroying it. It becomes a random process. It's never good. What if you say, well, I don't want to really destroy any parent by giving him an artificial mutation? Well, it turns out that biology does that to survive. Because there may be an evil race there that tries to come up with vaccines that will kill your genetic information. So if I was a coronavirus, one of my chances of actually escaping from this massacre created by these creatures called humans is to mutate myself. I'm trying to connect it to some daily terminology that you're using. So it does have a purpose in life, believe it or not. You may have heard that cancer in humans is because we have mutations in our genes and they are really harmful, but those are the harmful ones. There are a lot of other mutations that actually you don't become sick, but somehow it improves you. How does it improve? That's the question that I will answer with a little anecdote that I normally tell at this point in my lectures of engineering optimization course. And that goes back to the old sci-fi movie called Star Trek. Star Trek is, with your standards, ancient TV series that our heroes, Captain Kirk and his crew, travel in the universe with their starship, and they go to one galaxy and find creatures living on a planet in that galaxy, but they get very surprised when they land in this place, because everybody in the galaxy looks identically similar to everybody else. There is no variation in facial features or number of arms or number of eyes, or they are blue-eyed blonde people actually in that movie, but they're identical to one another. And when our heroes ask what happens, why is your population, your entire race is like one single person? And they say our ancestors eons ago lost the mutation possibility. So the best the person in the population at the time start ruling everything else, and at the end everybody start looking like that same person. We got stuck in a local optimum. That there was no way getting out of that local optimum. What the mutation does, it throws a kink in the search. It goes and explores new forms of whatever we are representing, whether it's a laminate or whatever it is. It just creates a kink and says, hey, what about this? Do you think this will improve? If it doesn't, it will die in the selection process later on. But if it survives, it goes into the next population. All right, I suspect I spent enough time explaining this, unless you have a question. It turns out that there are actually very nice ways of also doing mutation in the composite world. And they are called ply deletion and ply addition. So what you do in the laminate design optimization is you randomly pick a point, again with small probability, unless your purpose is to interrogate a lot of different thicknesses. And you pick a point, and you pick that digit into 0, which is an empty ply, and then pack it so that it goes to the outside of the laminate, and the resulting laminate will only be this much. So if you compare the parent and the child, what it did here is it actually mutated the second or deleted one of the 2 layers of zeros from here. So it reduced the ply thickness without disturbing the stacking sequence much at all. Okay, that's the important thing. You converge to some value of fitness that's really good because of the particular stacking sequence that really likes having zeros in the outside and 45s in the inside, and but your thickness is high, and by doing this, you're preserving the stacking sequence pretty much the same, except you reduce the thickness. Same way you can do ply addition, and ply addition is again a form of mutation, but in the composites case, you don't add a ply anywhere you want, because that may again change your properties too much. The best place to add it is to go to the ply that is closest to the inside of the laminate, close to the mid plane. So, for example, here I not randomly choose, but I choose the last location and randomly introduce a ply, which is 2. So this 0 shifts to the left. This length is the same, and new layup is 1, 3, 1, 1, 3, 2, and then additional 2, which is another 45-degree ply that you might be adding to the laminate. One last operator that is actually, I believe, somewhat unique to composite design. I'm honestly not sure if any biological entity does this kind of a mutation operator. We call it ply interchange. And the ply interchange operator in composite design takes the genetic string, randomly chooses 2 locations, and swap the plies between the 2. Now, can somebody tell me why this is unique to composite? And what does it do in terms of composites? What properties that you see before and after your ply swap operator that you think might be beneficial? That's a question for you now to think about. Any thoughts? All right, let me give you a hint. What does in-plane properties depend on? Pi angle. That is correct. So more accurately, total number of plies of given orientation. Okay? So if you look at this design and this design, there's absolutely no difference in the total number of plies in the laminate. So the location of the ply angle doesn't matter. So if your design problem has some feature that depends on the in-plane properties, it is much faster to converge to that design than a property that depends on stacking sequence. This design has 6 layers of 0. And this design has 6 layers of 0, 2 layers of 90, and this design has 2 layers of 90, and 2 layers of a pair of 45 plus minus 45, plus 45 minus 45. So in properties are identical. I shuffle this around any way I want, I get the same result. So from your initial design that was not near optimal, if your objective or some constraint depends only on the in-plane properties, the algorithm is going to find the total number of designs that satisfy that constraint very quickly. Because it doesn't matter where he puts it. As long as it gets that, it's going to stick to that. That design is going to become good. Shuffling it is not going to change. And you're going to converge very fast. But what this operator does is it changes the bending stiffness. And anything related to bending, vibration frequency, buckling load, bending deflections, it will change by shuffling the plies around. So it's going to fix this, and by shuffling these around, you're going to create more and more designs that have the same identical in-plane stiffness, so your internal load distribution may not change. It's optimized, but then it starts changing the relative location of the plies so that you optimize the bending-related properties. So this is rather a unique operation. And as I said, if anybody has an idea that natural genetics might have a counterpart of this, I'd like to know. My biology is very poor, unfortunately, gentlemen. In fact, almost non-existent. I know I have a hand and half of a brain. That's about it. I made my joke and I laughed, and then Siri and Alexa will laugh next. All right. Now I'm gonna do. Oh, it's 4 o'clock. I'm sorry. We're getting over. So instead of going to tutorial, let me finish saying one more thing. These are the very basic mutations. And this is called a one-point mutation. It's possible that you can do uniform mutation, taking each bit at a time, and with a smaller probability, you can start looking at if you want to mutate every bit or not, one at a time. That's called uniform mutation. There is a multi-point crossover operators that instead of crossing at 1 point, you can cross at 2 points, and actually let me do that real quickly so that you can see the nature of it better. This is important because it turns out that seriously 1 point crossover is really not very good. And laser, how do I erase things? Pen color, reset. No, I don't know how to erase. Eraser is not highlighted, so I'm going to make it blue. So you can maybe do 2 point crossover and say these two are selected as points, and then you put 1, 3 in here. And then you put 1, 1, 3 here from this, and then you keep 1 from the original one here. So this would be the 2 point crossover, and 2, 2 is here, and 3, 2, 3 is kept here, and this becomes 2. So that's a different design, and this can be increased to multiple crossover points, as many as almost the length of your string -1. So you can be doing crossovers at every point, flipping the genes like that. For composites, this honestly, I have never tried it personally myself, but it appears that changing these between the parents like this may actually have some value, but that's something that will need to be proved. But I know if 1 point is not a very good option for any genetic algorithm, especially for biological genetics, where your genetic strings, the DNA strings are so long that doing 1 would have probably created children that half of the child would look like mother, and some other half would look exactly like the father, which would not have been, I think, very pleasant. I don't know, would it? Nah, I don't know. I don't even want to think about it. All right, any questions so far? So this would actually pretty much finishes the lecture. Next lecture, I'm going to actually go into the tutorial. and do this with the composite laminates as well as some of the binary version of this, and we'll go from there. If not, I'm gonna stop. Is there a question? I heard.